thanks for joining this webinar. On behalf of IEEE Computer Society Execom Committee, I welcome you to the webinar. So today is the second webinar in the series. It's a joint webinar series between IEEE Computer Society and BITS Goa Center for Advanced AI Research. So two weeks back, we had a session from Dr. Sriparna Saha. Today's session is by Professor Bhabatosh Chanda from ISI Kolkata. He'll be talking on single image dehazing method. So previously, as some of you may notice, we had celebrating computing webinar series as well, many of them during May, June, and July. So welcome to Professor Bhabatosh Chanda. He is with the Electronics and Communication Sciences Unit of Indian Statistical Institute, Kolkata. And he's a very eminent professor in the field of pattern recognition and image processing and computer vision. He's a fellow of International Association for Pattern Recognition and also IEEE and many others. He will be talking today on the single image dehazing method, which is a very interesting topic. And some aspects of computer society, we've been in the forefront of leading from the front with many awards, both locally as well as internationally. So I would like the participants to follow us and join us for a lot of opportunities, be it as a member or a volunteer or a leader, or even for some of the aspects involving um, uh, expert lectures and all that. So do follow us through Instagram or Twitter and Facebook and LinkedIn. We are also updating all of our events through our website and email. So please reach out to us. Please feel free to reach out to us through these social media channels. We'll be happy to get back to you. Without much ado, I would hand over the virtual stage to Dr. Chanda. And before that, a few housekeeping stuff. So please post your questions in the chat window, and the speaker will take them up at the end after an hour's lecture. And we'll be happy to share more details regarding the webinar after the event. And also the feedback form will be sent out to you. And also updates regarding the upcoming events. So thank you and welcome you all to the webinar. Anand?
Yep. Thank you, Vishwas. All participants, you are muted on entry. Kindly stay muted and turn off your videos. Please post your questions in the chat window. I'll be monitoring them and the speaker will be answering them towards the end in the Q&A session. Over to you, Professor Chanda.
Thank you, Anand and Vishwas. And good afternoon, everyone. Let me share the slides. Okay. Is it visible?
Yes, it is. Perfect.
And I'm audible, right?
Yes.
So let me start with the simple thing. I should have written the single image dehazing, but to start with, we just talk about what this image dehazing is. But remember that I'm 60 plus old, and last 10 years I didn't write a single line of code to understand the reason. So all the results, all the algorithm detail is done basically by me. These two students, Sanchan just got his degree, and Ranjan is going to submit by next year. Now, we take pictures almost always. We have mobile camera and other digital cameras. And if there's a good bright light daytime or nighttime environment, we get good pictures, no doubt about that. But there are situations where the environment or the climate is not that good. In case of fog, haze or raining. We have low quality pictures, and mainly problem is the low visibility and color is dull. Okay? Some particular color may be dominating. For example, in the haze image, we see some more like a greenish. Okay, so what is image here? Given the image on the left, this original image, this is taken under a little hazy situation, and a computer algorithm will convert it to the picture on the right, we call the dehazed image, and this is much better quality of the earlier original one. And secondly, if you want to go for some uh, computer vision or image analysis or scene analysis algorithm, so obviously the dehazed image will produce a much better result than the original ones. There are many other applications where the uh, transportation, etc., is involved, and where cloudy or foggy or hazy days is a bottleneck for running your car on the highway at a higher speed. Okay, you can use that. There is another example of this given the nighttime hazy image, and you can generate the original TSD. Both the results are from our algorithm, but I'll come to later the detail of this. So what is the objective of this image de-hedging? Okay. So basically, it improves the quality of the image taken under the bad weather conditions, right? And we mainly focus here on the foggy climate or the hazy climate. Okay. So goal is the scene restoration mainly, and as a byproduct, we can also estimate the depth of different objects in my scene. But sometimes this is a kind of chicken or egg problem, which comes first. Some algorithm first get the depth estimation that restores the image, and some algorithms restore this image, and from there, if you want, you can estimate the depth to some extent. Okay? So outline my presentation is with this introduction. I'll first talk about the image formation, because that will give you an idea. There's what should be method or what's the actual root of the problem, how we can handle it. I'll talk a little about the existing methods, followed by our method, and I'll try to take care of two different approaches. One is based on the complete traditional way. There's a from the model, imaging model, I want to will try to exploit some of the physical properties of the scene or the environment or the image and try to solve the problem. And second one, we all know this is a more recent techniques, uh, deep learning network, and that is based on the example, based on the training data. You can train your system to get the solution. And finally, in the conclusion, we'll talk about the pros and cons of both the approaches. Okay, now let's how the image is formed. For forming any kind of image, you must have some objects in your scene or the scene itself, and you must have a light source. In the outdoor scene, daytime sun is the uh, most prominent and the predominant light source. And suppose some light is incident on the object, and based on the reflecting coefficient of the object, the lights are reflected in different directions, and a particular direction, the direction where my sensor or camera is there, some light will reach here. So considering the completely clean environment, what happens, the whatever light comes from here will reaches at the camera, and that is recorded. That is observed intensity. So we call it the reflected light G of x, and the recorded image is the I of x, where x is the coordinate in the 2-dimension because it's a 2-dimensional plane. Now, there are many floating particles in the atmosphere, in the climate. Okay? There may be air molecule, maybe water droplets, darts, etc. And what happens when an incident beam of light or a ray of light falls on a particular particle, it scatters. Now, the scattered beams means the light which should have gone in the straight direction, instead of that, it diverted in many different directions. And a particle in the part of the light scatters the incident light depending on the size of the particle and the wavelength of the light. And there is a good study from McCartney in 1975, and it shows that there are different kinds of particle floating in the air. It could be air molecule, haze, fog, cloud, rain, and they are different sizes and their concentration in per cubic centimeter in the air. Okay? So depending on that, the amount of lights scatters in a particular environment. We are mostly interested in haze and fog, where the we call the aerosol or the water droplets, and their sizes are roughly from 10 to the minus 2 micrometer to 10 micrometer, and this is the density. So here are some example, the clear sky, but probably you know about the Raman's effect. That is basically because of the scattering of light in the upper atmosphere, uh, hundreds of kilometers above the Earth's surface. But we are mostly interested in very close to Earth's surface and a few kilometers from the ground. And here mostly dust particle, water droplets predominates the floating particles. So this is an example of white haze. Here the color of the floating particles are little different. Scattered light is different, is something like a kind of hazy. Okay? So what happens theoretically? From the object, some light is reflected, but because of these particles present between the object and the camera or the sensor, the floating particle scatters the light. So light cannot reach, full light Jx cannot reach the camera. Only a part of it reaches there. This part or the partiality controlled by the T of x, we call the transmittance. So this transmittance lies between 0 to 1. Which is a 1, the complete light reaches the camera. Which is 0, no light reaches. So it is usually below, between 0 and 1. It's practically it's closer, more than 0.5 usually, the T of x. And it also has some bias to add to it. How, from where this bias comes? Let's look at the situation first. This Tx actually depends on the distance. Higher the distance, you understand more scattering, less light will reach us here. So Tx depends on the distance. Higher the distance, you have the lower value of T. And beta is actually controls the scattering effect, where D is the depth. Now, fine. So some light is really getting scattered, is not really reaching in the camera, that you understand. At the same time, some of the environmental light not really coming to the object itself, but from the floating particle, they scatters and automatically reaches the camera. So this is the additional light, which is not really coming from the object. Some additional white light reaches the camera, we call is the air light. So this air light is nothing but this 1 minus T of x, that is the less than transmittance, and A is actually the environmental illumination. So these two together generates a kind of observed image where the color becomes dull, and because of this one and some additional white bale light white veil-like or the curtain-like appearance, the color appears in our image. So this is my hazy image. Actually, I get one. And what is our objective? Given this IX, given this observed image, I have to estimate the J of X. I don't know exact value of T. I don't know the exact value of A. Right? Let's look at only the problem, the mathematics behind this. Right? I'm not going into much detail of this one, but to give you just an idea what fits with the just high school mathematics plus 2 other mathematics. Okay? So this is my equation. I have I of x observed image. I have it, and I want to estimate j. That's the original image. That should the best quality image. But I don't know what is the transmission value, transmittance coefficient. I don't know what is exact value of environmental light. We assume here, since the color image, I has the component red component, green component, a blue component. J also have the red, green, and blue component because any color is made of mixture of 3 different primary colors, red, green, and blue. A is again environment light is C by 1 vector, red, green, blue. But the TXC is a transmittance. It is basically scalar. And the environment light is, we assume, is a uniform over the entire scene. So it is very suitable, very real in case of outdoor scene. Take the image is taken daytime, okay, where source is sun, so A is constant over the whole scene. Now we see how many unknowns are there. I have unknown 1, T, unknown A, and unknown J. Only thing I know is I. So a single equation with this color. So 3 equations. So for color red, green, and blue, we have 3 equations, but we have how many? 7 unknowns. 1, 2, 3, 1, 4, and 1, 2, 3. 7 unknown and 3 equations. Or if we just condense it to black and white image, even then it's a 1, 2, 3, 3 unknowns and 1 equation. So it's an absolutely ill-posed problem, and getting solution is very difficult through use of linear algebra and other methods. So this is being tried for a long time, more than a decade, but people started working with the multiple image or the single image, but depth map is available. Or very recently, people are working on the single image, which is more feasible, more practical. And for each of the cases, we either require some kind of user interaction and some algorithms are fully automatic. For example, our algorithm is we try to do it fully automatic. So we are mostly interested in single image dehazing method, which should be fully automatic. Now, if we look at the earlier approaches, earlier items, there are very good algorithm which assumes more than 2 images are available, and from there the number of equations increases, and so number of equations to number of unknown, this ratio becomes more better than the single image. And there's a very early work by Narasimhan and Nair in 2001 that gives a very good result. Another approach uses a polarization filter so that same scene is being imaged. The image is being captured with different filters, polarized filters, so that different images can be obtained. And as a result, what happens? I can get even more number of equations, and so that getting the real solutions is much better than having the single image. Okay. So in an example of the Transmittance image, is taken the same scene, but two images on the two different gears. Okay, so their hazy component is different, and this is the dehazed image, the C, which is a little darker, and you can look at the one image which is taken as a not so hazy day. Okay, you can compare these two. It's a very good approximation of the original ones. Okay. In one image and depth texture is a SIGGRAPH 2008 is a very good result, which is a very good result. But its problem is it assumes that 3D information model of the scene is given, okay? Which is very difficult to get. But they assume that from the Google map they can estimate that. They assume that from the satellite or the aerial photos, they can estimate the texture of the scene over some time. And they require some kind of user interaction to align all this 3D model, texture, information with the captured image. And as a result, they got fantastic result. But remember, they require so much information, which is not really available, not readily available. Okay. In case of single image approach, this is a much more recent ones. They don't require any information except from the additional image. Just one single image is good enough. And they don't require also depth information so that they can have the transmittance value at least to some scale, which can be estimated from the depth. You just remember, just T is equal to e to the power B of dx, right? And D is the depth information. So if I can assume beta, I can calculate T and I can use that. But this is the single image unit approach does not use that information. Okay. And typically this kind of approach assumes some kind of statistical assumption or some kind of user experience. For example, most of the outdoor scene may contain a part of the sky also. Okay, so this kind of algorithm is very suitable in the images where at some part of the sky is visible. When I discuss one of the algorithm, I'll show this of how this sky part is important. Okay? Sometimes they require user interaction, but most of the cases of automatic algorithm can be developed. And two benchmark algorithm was proposed. One is the SIGGRAPH by Renner and another is the HE. So in 2008 and 2009, and we'll start talking about the second one, the 2009, because it remained popular for a long time. Okay, it's called a dark channel pair. Okay, so suppose this top one is the original given image. Okay, it's not a hazy one, just for the demonstration purpose. Given a natural image, top one, and every pixel has the color information, red, green, and blue. Find which is the minimum value of this color out of red, green, and blue. Right? So then, over a small area, small patch, find out which is the minimum of this minimum RGB. Okay, and that makes the bottom one. So from the original one, we find out which is the minimum of red, green, blue, and this minimum is again in the minimum over a small area, and find out this one. Okay, what does it give? This gives at least this much light has fallen on this cell. Okay, at least this much light has fallen on this natural cell. The amount of light may be more, but at least this much is there. So if I can find out we combine this simple mean over mean, we take that is the dark channel of this scene. And that gives you the basically dark channel information or the backlight or the air light information to some extent. Now, in an image, if we have a sky part, what will happen? The sky has the largest distance, so it has the brightest color. And what happens if I take this, we can find out the sky portion, then we can say that this is the air light fallen or incident on my scene. So what you do, what the algorithm does, algorithm takes that this dark channel and find out the highest 0.1% area, and that portion may be given the white or the air light of the scene. So this 0.1% bright pixel gives you the air light or the brightest portion of the scene, and that is your A. Now, once you know this A, you can somehow estimate the transmittance by rearranging the same equation, the equation I saw earlier. Okay. The equation I saw earlier, if I get some kind of A, I just try to estimate the transmittance from that scene. Okay. So here is the example. So this is the scene. It tries to find out air light and finds this is the top portion, which is more or less air light. So that gives us some kind of the A of A color, and that is okay. This color here is to show this basic intensity of light. Not really everything is red for some reason. Air light is red. This basically shows the example of kind of air light received by the sun and the depth also. So, which is the limitation of this algorithm? This algorithm assumes the color is the pure color. What it means? It's a saturated color everywhere. The pure color means red and pink. We know both have the same hue. That means the same color component, but pink is more whitish than the red. This particular dark channel color algorithm assumes that my entire scene is completely filled with the pure color. That is, no pink is there. If red is there, only red is there, no pink. That is a little bit unrealistic. So many cases, this gives an unnecessarily contrasted color in the scene. It also assumes that air light is uniform all over the scene, but many times you see the sun ray coming through the branches or the leaves of the tree. So in that case, the air light is not really uniform. Especially in case of light, there are many different uh, illumination sources, and in that case, this particular algorithm is not really useful. And it's assume that some part of the image should show the sky. If the sky is not visible, this algorithm cannot really estimate the air light, it fails. And what I said, just because of second and third, this algorithm is really applicable for daytime images and not really useful for the nighttime image. Okay. So just I'm showing them an example of the result of fatal. This is the hazy image taken the daytime, the image taken daytime, and you got the dehazed image. It's a fantastic one, very good result. But it fails miserably when I convert the nighttime image and try to dehaze it. It absolutely fails. On the other hand, there are algorithms which talk about only nighttime dehazing problem. And in that case, it gives more or less good result, visible result for the nighttime dehazing. But though the result is not very natural, there's so much textured color is there, but it absolutely fails in case of is not look like anything realistic uh, output, okay, in daytime dehazing. On the other hand, our method is what I am going to tell you right now is some kind of in between. It works more or less okay for the daytime, more or less okay for the nighttime also. Okay. How do you do it? We take the help of a particular concept called the color line concept. So dehazing is done based on the color line. Okay, and this color line concept will work for the both daytime and nighttime images, and real light is assumed to be very spatially. So this is not really uniform, the constant over the entire scene. It varies, but very smoothly, varies very smoothly, not very abruptly. Okay? And so we modify our image formation model accordingly. Okay? So you see, this is an example of nighttime image. And there are many different sources of light, okay, to illuminate in the scene. So what you do, this is the given image model. A is the constant all over the scene. Now you convert it to A or the L light to be varying over the spatial coordinate of the X. X means the both X and Y vector. Okay? So the L light varies over the X. Now this varying L light, we assume this has two components. One is the magnitude and the direction. So anything varying, you can have its magnitude, the direction along which the light is being illuminated. So this equation, one of the original equation is modified like this too. So we see this Tx is the scalar quantity. 1 minus Tx is scalar, Mx is scalar because it's a magnitude. So you can merge everything together to get A, and the E of X is the direction of the varying line. So now again, we still have the problem with one equation with 1, 2, 3, and 4 unknowns, but I have some resource to solve this even worse problem. So this is my equation. Okay, so this equation is under constraint or ill-posed, and because we have only Ix is known and all these J, A, and Ax are unknown. Okay, so we do two things. We assume that within a small patch, small area, all these things are uniform, the constant. Transmittance value is constant, this magnitude of air light is constant, the direction of our light is constant over a very small patch. I will give you the example. Okay, and second, we use a color line plot to introduce more constants. So it is more constant to solve the problem. The basic idea was once given by the Fatal, but he's not really given any existence algorithm. Now, look at this natural image. We can have very small patches here and there, 1, 2, 3, 4. Now, if I look at this sky portion, very small patch, you see all the values, if I blow it up, all the pixel values are same. If I take this one, this small patch, all the pixel values very close to each other, very same. If I take this one, the picture value is little bit quite different, varying. It's not really very uniform. And if I take this small patch. It's a, yes, it's not this much variation is there, but it's also not the kind of smoothness we find here. So suppose here in this blue block, there are say 100 pixels, right? Uh, Now each pixel has the red, green, and blue value. So if I put this red, green, and blue value in a three coordinate system, red, green, and blue, we can have a single point in this RGB space. So since all the values are same here, what will happen? They will concentrate a particular region only. Whereas since here there are too many variation in the pixel values, they will scatter all over the RGB space. Okay? Let's look at this one. Only consider this one. This is a little bit of variation. This is a little bit of variation. And if I plot these color values, each pixel in my red, green, and blue space, it is scattered something like this. And I can fit a line which passes always through the origin. So very good color image with no haze or no degradation, no noise. Ideally, every small patch, all the color values will be scattered within a very small area. And if I make a estimate a line through it, through all the points, that line will pass through the origin of RGB color space. Now, if I add some haze, what will happen at each and every pixel, some white color is added and the contrast of color is low. So what happens? It spreads to have more whitish light and more color variation. And if I fit a line, the line no more passes through the origin. Okay, origin is here, it doesn't pass through the origin. So the shift of this line is because of the adding of the haze or because of the hazy color or hazy weather. So consider the RGB values of the pixel in a small patch. The ideal line a small cluster in the RGB space. In reality, there are on a line passing through the origin in reality because not all the colors are really same. But due to distortion by haze or fog or rain, they form a much more elongated cluster, and this cluster fits a line which is far away from the ideal line. From here, it is this movement is along the direction of tail light. So if I know what is the direction of this shift, I can calculate the direction of the tail light. I'm not going into mathematical detail. The physical interpretation of that, any good color patch, if I plot it in the RGB color space, the line fitting through those values passes through the origin. If haze or fog added to the picture, the line shifts, the color line shifts along the direction of the air line. So from there I can estimate the direction of air line. But how? Question is how I can estimate the direction. Now suppose given these points are fit the straight line. You know there are many different methods for fitting straight line given a cluster of points, right? The simplest one you have learned in your high school mathematics statistics is a linear regression. You can do it, right? I'll take a different method. It's called Ransac method. There that can fit computationally more attractive algorithm and it can fit line through the cluster of points. So suppose there are 2 points selected. I1x and I2x, through which the line passes, which is my color line that fits into this. Okay. Now, these are the 2 points, I1x and I2x, through which the line passes. And I have another point, well defined, that is the origin of the red, green, blue splits, RGB color coordinate system. Now there are 3 points, I1, I2, and the origin. I can fit a line, fit a plane. Given any 3 point, I can estimate or I can determine the plane. It's again high school mathematics. So once I can calculate the equation of the plane, I know this direction of light will lie in that particular plane because the line passing through the origin is shifted by this A to that I1, I2 line. So this plane contains the. Now suppose I take another patch, and that will fix another plane. Now both the plane will contain that direction of the light because that is common to all. So what happens? There are 2 different planes because there are two different patches, 2 different cluster, 2 different color lines, say L1 and L2, and through them I can get 2 different planes, and these 2 planes should intersect at some point, some line. 2 planes intersect along some line, and that line is the common to both the planes, right? It's a simple geometry. And what is that? There's the direction of color, error light. There is the direction of error light. So I can, from the multiple images, multiple image patches, I can estimate the error light and take the average of those all the directions as the overall direction of error light. So it's as simple as that. Now, once I get this error light, I can have this m of x, or the magnitude of error light, say rho, in such a way so that that can be estimated from the same plane which is normal to the both the things. So I can estimate both the magnitude ax and the direction of error light for some patches. The problem is I cannot do this estimation for all the patches. Reason is very simple, because not all patches have shown that kind of color variation. In some cases, remember that blue patch particular in the sky area, that takes practically all pixel values are very close to each other. And that will remain in a very small cluster, circular cluster, so that I cannot really fit any line with confidence. All possible lines are equally fit to that circular cluster. So I can neither estimate direction of light nor the magnitude of light. Second, some patch may contain a part of an object, contain part of another object, some patches. And if those 2 objects are at a different distance, their Tx will be different. So Tx is not constant for the patch. There are other problems. There's some color in the image is similar to the direction of the air light. For example, my environment light is white, okay? And you have taken a picture, it contains a building which has a wall which is also color white. So yellow light and the color of the wall is basically the same. They will show the same color direction, color line direction. So that will be confusing. So for those patches, we cannot really calculate the direction of light nor the magnitude of the direction of the air light. In those cases, we discard those patches from the estimating the L light or its magnitude. But we need to estimate the direction and the magnitude and the transmittance at each and every point. So what we do? I estimate the patches from where color light and magnitude is possible, and rest will be interpolated. Okay, rest will interpolate this NX from which I've already estimated patches we have already estimated. So in my image, I divide into many small patches. From some patches, I can estimate the L light and the magnitude. And from some patches, I cannot estimate that. We ignore them, but I estimate or I generate the L light direction and magnitude from those we have already estimated. From there, we can interpolate and generate the value there. Okay. So I am not going to enter any detail. So we assume the something is a very ideal one and something we have already estimated. So from there I can estimate the so that the second order derivative remains smooth. L represent the what you call the Laplacian or the second order derivative of the uh, smoothness criteria, and that is ensured to get the estimated one. Similarly, we do the AX. I'm not going into detail of this mathematics, and that will. So now I've calculated the L light direction and the magnitude of the L light. So I can estimate this one AX and is all are estimated. From there, I can find out the G of X. So G of X of Tx is this one, but I don't know the Tx. So I have to divide it. I assume that for white light, what I can estimate this one as a Y component. This is a very standard color image processing technique. There's from RGB image to I can go to YCBCR, and from Y I can simply what should the maximum transmitter, the correcting coefficient which can enhance the contrast of the image. So we can use that one to estimate the J-prime matrix. Okay. I'm sorry, considering the audience, I'm not really going to detail. So you can look at our papers where all the details are given. So this gives a very good result for a large set of images, but still, since we are putting some kind of heuristics at this level, we cannot really analytically guarantee that it will always give a good result. But most of the cases, it gives a good result, right? Okay. So this is the original hazy image. This is the result of Lee. This is the result, and this is the result of our method. This is actually designed for the nighttime image. Here is another nighttime image algorithm. This is the original image. This is the Lee et al. This is a much more contrasted. You must agree, but it's a little bit unnatural. This is a little much better contrasted, but on the other hand, daytime, this is a given image. There are different result of different algorithm. This is our result. Okay, little yellowish. Here is another example. There is the original image. This is a pattern. It's a good one. Followed by this. This is a bad result from the layer. Okay. And another result, hazy image. You can clearly see the results. But sometimes we have failed. Is somehow our image has gone the blue tint, additional blue tint. We don't know from where it came. Patel gives really good result because it's a daytime. Another result is again this gives Lee gives the best result. Patel is not that so good. or is again the blue tint. Okay, but it gives a much better quality. Now, very quickly, I go for the deep learning technique because not much I can explain it here using the so-called deep learning method is based on the examples. Lots of examples are required. Now, we say this is based on the comparator. Why comparator? Suppose you are given this particular image patch, and you are asked, there's can you tell whether how much haze it is, whether it's a hazy or not? If it's a hazy, it's a really hazy or not. How much haze is there? It's very difficult to answer, I know. But if I give you two images and ask you between those two, which has more haze, you can immediately tell, okay, the left one, right? So an comparator can tell me whether an image patch has haze or not. Okay? Or more generally, whether an image patch is a good quality or the bad quality. So what is our objective? We try to develop a comparator. Comparator of these patches, given two patches, I will develop a comparator which will distinguish between the good quality patch and bad quality image patch. The work is published in the IEEE transaction image patch in 2018, recently 2 years ago. And so this comparator is tuned especially for the distinguish between the hazy or the bad patch and the dehazed or the good patch. Okay? And in doing so, practically we can estimate, by the use of this comparator, I can estimate the transmittance and the L light from the hazy patches. Okay? So don't take this hazy patch, this comparator is anything very different from the kind of deep convolution neural network available in the literature. So it's not very different from that. You'll see there's practically is a two-class classifier. It is practically a two-class classifier, but we just use it very novel way to distinguish between the quality of patches between hazy and not so hazy patch. Okay, so we need to train the comparator. What is our principle, or how do we do it? Suppose we pick up a particular patch from the given natural image. We deliberately haze this one. We apply my haze formation algorithm, supplying the value of t, supplying the value of a. I can easily make the hazy this patch hazy. Now, this is a good patch. I made a hazy patch. Then from this hazy patch, suppose I don't know what is the value of t, what is the value of a. I just put some value of t and go try to dehaze it. I'll get different result depending on different value of t. Right? Now you see, some of the results are bad compared to this one or this one. Some are good compared to this one, or some are bad compared to this one. So I already know which one is good, and I deliberately generated some good patches and bad patches. So I have lots of such patches, and I can train my comparator in such a way that it can learn how to distinguish between the good patches and bad patches. So basically, I take the original patch, haze it deliberately, Then I put different A and T values and just went on dehazing and take this as the our output of the patches and then put as a good and bad patches, pair of patches to my comparator and try to estimate, learn that. What is the lump? Okay, there are two input patches. One may be good, another is bad. Put them together, make some convolution of size 3 cross 3, 32 of such kernel, generates the result, then the size reduces. Then I take again convolution of 3 by 3 kernel, 16 such. Then I get this one. Or I go on doing this at 2, 3 levels. And then from there, I put everything this output for first image, output the second image, putting together, flatten them. And all these are very standard technique, nothing very novel here. Just use it very novel. Okay? And making it is a some kind of dense network to make a classifier, the good patch and the bad patch, class 1 and the class 2. So my chain of classifier is trained. Now, once the classifier is trained, I try to dehaze my unknown image using this comparator. How can I estimate the T? Since I don't know, just suppose this patch is, this is a test match. Forget about it is used in the training. Suppose this is the test patch you are given, right? I have to find out the value of T given this one because I don't know T. I want to dehaze this one and that requires the value of T. And I don't know the value of T. The one way I can do, try to dehaze this one with the 0.99, 0.98, 0.95, so all possible values and try to compare with this one when it's a good or bad. Till it goes to good patches, I take the particular value of T and then after that it starts being worse and worse. I stop there. I take the best possible quality of patch, that corresponding value of T is my value of T. But that will take lots of time. It's a linear search and will definitely take theoretically infinite time. Okay. So rather, I will apply the binary search. What I will do? I'll start with the 1. 1 means that Tx of x is 1. So 1 minus Tx is 0. So there is no Li. I have only the confidence level, the transmittance value 1. Now I apply the 0.5. So there is another patch. Now compare these two. There is the hazy patch, there is the DS patch. Whether this DS patch is good or bad, if it's a good, I will go even reduce it further. If it is a bad, I will increase the value. Suppose it is a bad, the compare this and the DS1 and the good or bad, then I will come back. I'll get another. Now compare these two, whether it's a good or bad. If it's a bad, then we need to increase, and if it's a good, I'll go on decrease the value. So if it is a good or bad, I can go on, then half, then half, then half, just like binary search, I try to estimate the value of T. Once I get the value of T, I can estimate the value for the, if the step size is small enough, I can find out the value of T as a good one, and that will help me estimating the dehazed image with the T. Okay? So this is our method, works for both because it's a no color model, no information model, just given blindly 2 pair of patches and from there it goes on. So what is the algorithm? I'll divide the whole image into multiple small patches, give it to my comparator, with some value of t and try to estimate the value of t and apply that one on my patches of the given image. I can dehaze this one. This is another result. This is the hazy image. This is the dehazed image by fatal, dehazed image by our method. Look, this is a comparable. And the advantage is fatal is good for the daytime image. It requires lots of estimation, but I can use the single comparator to find out any kind of information. Okay. So what we have done? We have done two different approaches. One is the color line based, which takes care of the image formation model, some physical concept, and try to analyze this one, the de-aging problem, at least so that you can handle both daytime and nighttime hazy images. Okay, that's one advantage. On the other hand, I have a 10 comparator can distinguish between good and bad quality patches. I don't care about the image formation model or any physical criteria. I just improve the quality of the image, and this can be applied to many other image improvement tasks, right? Now, still we have algorithm have way to further improvement. For example, we assume there's some kind of real light computation we have got from other methods, say from color line method, we have computed the real light part. Only Tx, which we assume earlier case, color line case, we assume Tx or the transmittance, that is calculated the computer here, but we want to generate a comparator or a network which can handle both T and A real light simultaneously. Okay? And here, so this comparator we have stopped when this actually the search step is very small, but we did not really approach at the correct value. Can we make some kind of more accurate value through this network? That is another problem we need to look into it. Okay, and here are some of the important references. Already I've talked about the Fatal, Lee, and Hay. This is one of the early methods. It also take care of the color lines. And we have two papers in this. So one on the color line is the ICPR paper, and on the comparator is the IEEE. Okay, thank you for your attention. I'll be happy to answer the questions, right?
Thank you, Professor Chanda. It's been a really informative session for all the participants. So participants, please post your questions in the chat window, and the speaker would be glad to answer them. So to start, Professor Chanda, so what is your take on the non-local image dehazing? Because I think that is also coming up very lately, right?
Right. So non-local, this our algorithm you have seen this basically contains assume this small patches contains the uniform transmittance value, uniform the real light, etc. In case of non-local, you have to really look into the whole image at a single go. And one of my students is working already in the CBPR workshop they has published, and that takes care of basically the larger patches. This is the non-local means takes a large patches, takes care of multiple objects at different distances, and that this is a competition more intense. But even then, I would say this is a very difficult because it's a ill-posed problem. You cannot really have a very good analytical solution for the non-local algorithms. Okay.
Okay.
Hmm.
Thank you. And also regarding the data sets that you use, do you make use of any particular data sets, or do you make any of them available for others to explore? How is it?
Right. Okay. I'm sorry. I should have included that information, but unfortunately, I told you for my first slide even. Actually this all the work is done by my students, right? And I know there are at least three different uh, public domain benchmark data set available. I'm
Okay.
sorry, I cannot give you the reference right now, but if your members are interested, I'll definitely get those websites and mail it to you, right? Sorry for that.
Sure, sure. Thank you. So no problem at all.
Hmm.
Participants, if you have any further questions, please feel free to ask them by unmuting yourself, or you can also paste them in the chat window.
Yeah, do we have any more questions?
So I think they don't have. So Anand, you
Yep.
have a couple of questions for Professor Chanda?
Yes, I do have.
Yeah.
Okay.
Thank you. Go ahead.
Yeah, Professor Chanda, this is not anything like technical at all. Like this is more of rapid fire kind of questions for you.
Okay.
Uh, so the first one is, what changes have you observed in the field of study of AI and ML in the past, maybe say 10 years?
Hmm.
Something that is very interesting and things that might have changed that you have observed over the years.
Okay. I would say very the bright side and the dark side also. Okay. Um,
Okay.
once this deep convolution neural network or the end-to-end deep learning network have come up, people have taken it as a solution for each and every, right? They think that if I have the large set of training data and I can train any system and I can get the result. Yes, surely some good results, some uh, very good superseding results has come out. I don't disagree with that. But the problem is, suppose uh, I have specs, right? I usually wear my glasses. If I drop my glass either deliberately or by accidentally on the floor, what will happen? It will fail. It will broke, right?
Correct. Correct.
It will broke. You just answered immediately. But if I ask you, how many instances have you seen that you have seen the people has dropped his glass on the floor and it broken? Almost none,
Mhm.
right?
Correct.
But you have derived that this space is made of a piece of glass or two pieces of glass, some the celluloid or some metal frames or anything with that height, if that is the concrete floor, if this is the impact value, there's some everything is computing very quickly, right? And you are coming to this, it's not real, it's only from the example, right? Many of our thinking process is not only just based on the example. Right? You may tell this, okay, the NIST data or MNIST data, handwritten emails from many different example. Well, we can solve it because this child has gone through A for Apple from many different books, many different font size, many different font style, and so on and so forth. So many examples helps surely, but not it's a what you see this progress in machine learning network and machine algorithms are going on, of course. But at the same time, many people are using it blindly, absolutely blindly, without really understanding what they are
Mhm.
doing and why it will work.
Correct.
Suppose you have a stomachache you are just burgling in a medicine shop and find out on the rack shelves there are many medicines and just take one and just gulp it.
Sure.
What will happen? It may give you a very good result. It may give you the very confusing and the very bad result. Okay? And
Correct.
you cannot
Correct.
explain. We have to really come out of that.
Mm-hmm.
Machine learning algorithms are good.
Yep.
They are they are have to be used very wisely, very cautiously. Okay.
Sure. Yeah,
Many,
even I do totally agree to that, sir. It's like everyone is using it for like so many different, like even simple if cases they are now trying to like.
right. There is a simple process. Even a matrix inversion can do it. People go for the machine learning. Secondly, another point is
Sure.
so look, this machine learning concept was maybe these words were not there. So it was a
Mm-hmm.
very well established in statistics, mainly statistics, all the regression methods and other things. Right? What is the
Okay.
machine? Either doing the regression or doing the classification, right? All
Correct.
things are present. Now, earlier, what you do, you try to find out some kind of uncrafted information, then try to feed your function into that. Now you are putting some kind of automated feature extraction and the classification of the regression so that you can get much more comprehensive output result, right?
Correct.
So problem is if I don't understand the basic or the domain or the cause of the problem, it's a very difficult to choose the right kind of network even,
Mm.
right? So
Yep.
people have to understand before the so otherwise it's a very good technique, well studied, and people are really a majority of people are working on it. It will definitely has a very bright future, even for at least for next 10 years until something comes to surface it.
Sure. Yeah, that was totally enlightening. Sir, I have another question. So,
Yeah.
what factors created an interest for you in AI ML research? Just something that was
Okay.
interesting that uh, made you turn to the field of AI and ML.
uh, look, again, AI has the different steps, right?
Correct.
I should not say steps, I should say stages, right?
Correct.
I started working on the this area, what you call the AI or the people terms. So almost uh, 40 years ago, after doing my BTech, I joined in the PhD program. I worked, my thesis was the image processing at that time, and I had
Mhm.
to use lots of pattern recognition techniques at that time. But I had to go through the AI books at that time.
Mhm.
People were talking of the Turing case and other things, and people were, and so basically, we really but I excited that there are many problems which
Mhm.
can be done automatically without any human interaction. And
Mhm.
of course, there's some of the things is already you can see in the even in the commercially the face recognition, fingerprint recognition, the computational pathology, your red blood cell count, this and that. Many apps or softwares is already commercially available. But when we are talking about the much more complicated problem, what we see that those conventional AI is not really useful. So people started talking about that. Is
Mhm.
I would say at the mid 80s that no AI is no more is a buzzword. So AI cannot really make human replacement or anything. We have to have some more what you call that. They started talking the computational intelligence. This again the same AI is a new name,
Mhm.
computational intelligence or some other thing. And some
Okay.
people call the soft computing. Um, and this and that, right? Okay, machine
Correct.
intelligence many things comes at that time, and people started working. They use the same classifier. Now the more is more like a neural network is coming dominating a major portion, and now people are thinking, okay, we earlier what we had to do, we had to really build our classifier based on some statistical analysis or the multivariate calculus. Now we know the network which can adjust the weights to generate a boundary function, either linear or non-linear, but the weights either it can set automatically. Earlier we had to calculate it through extensive, exhaustive method, some algorithm. Now it is started automatically. So the second phase of AI is going on. After some point of time, people says, no, 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 this is not that. We have to think of the not the actual optimization, which is the approximate optimization. Okay, and that is also really true. So many times your computational world cannot really reach at the optimal goal because you can't really formulate your problem in that analytical sense, right? So people talk about the computational optimization, and this computational optimization, approximate optimization, now the genetic algorithm, swarm intelligence, everything has come up. Now suddenly at the beginning of 2000 or so, people suddenly find out okay, all the operators are convolution function which people are using on the image by the min filter or the edge detector, that can be generated automatically, what you call the convolution network, and the mask or the weights in the kernel which were actually designed by people, whether it's a Gaussian window or Laplacian window. Now it will be adjusted by the network, neural network. So this is a kind of convolution theorem, constant algorithms used by the image processing people and the neural network making some kind of fusion, and your convolution neural network come up and gives a fantastic, the revolutionary result, I would say. And that brought again another jump, another create another kind of interest in the deep learning. And people slowly switch over. Do you think it's but even when in my lab, all the students, whenever any problem arises, just a frankly speaking, whenever I assign them a problem, after a few days trial, not even a week, few days trial, they come up, sir, should I attempt an autoencoder? So I always wonder why autoencoder there. They don't have a clear answer, but this is a most simple algorithm available on the internet or in the Python. They can easily use that. So that kind of, so people slowly being habituated with this one. So basically two things, the current technology and the complexity of problem we are dealing with. So we are really talking about that. The kind of, if we just think of the three-dimensional vision, right, computer vision.
Correct.
Now we can have a plugin in the, you can find in the internet, you can find a free plugin which can reconstruct 3D objects if you can give a set of 2D images, right? It's available.
Correct.
In 80s, people were hitting their heads on the wall to find out the appropriate geometry and they are just thinking of talking about the reconstructing the simple rectangular block or a hexagon or a simple chessboard pieces. That's a remarkable thing at 80s. Now you can anytime just within a tweak you can reconstruct that to the using a plugin. Right? Now we are talking about the whether we can reconstruct a very intricate temple or not, where all the 2D data may not be available. right?
Yep. Sir, next question is kind of more generic. So, what do you do in your free time apart from working on some project? When you're like absolutely free, you are sitting idle.
I don't get your question. Again, please.
Yeah. So, when you're sitting idle, like you are doing not working on some project or something, what do you do in your free time? Like when you're sitting idle? Because now we
Oh,
can't
oh, oh,
go out or anything, so we'll be
oh,
sitting at
right.
home,
No,
right?
no, 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 no. Mm, for your information, this lockdown period, the coronavirus is really didn't change my lifestyle. Except I cannot go to theater hall. Except I cannot go to restaurant.
Okay, correct.
Given this, living this too. What
Okay.
I'm doing 4 months ago, I'm doing exactly the right thing now also. Because I have to do a lot of administrative work in my institute. I have to guide my students. All can be
Yep.
done through emails and other things. And I completely segregate my working hours. That may be almost at 10 hours, but from my personal life. In my personal life, still I play a little bit of video game. Don't laugh. A little bit of
No,
video
no,
game.
sir, that is absolutely interesting.
Some Sudoku or some storybooks, some time with my family, my son, my wife, and other things. So my things is not really changed. So there are many things to do. I don't think me as a some kind of going to be depressed because of corona. No, I'm not.
No, no, sir, not that way. Like, we would like to know what you generally do in your free time and
No,
like how you enjoy time
no.
outside of
I
work.
outside of every there's a newspaper in the one Sudoku that I do.
Okay,
Some video game, basically, yeah, card games. I do some pre-sale or something that takes some time. Some storybooks, some movies on either Prime Video or YouTube or somewhere, and rest is my family.
sure. So since you mentioned movies on Prime, uh, maybe would you like to let us know which is your favorite movie, which covers a lot of technology, which you think that which you might have come across and you felt like, okay, this is awesome.
Ah, sorry, this part will not interest you. Look, I am telling you why.
Okay.
Look, the whole 10 hours in my working place, right? Either I'm in the office or though I come to office almost every alternate day, even in the lockdown.
Okay.
Uh, but if in my home I have enough laptop, desktop, I have enough arrangement there, so I can do it there also. So almost 10 hours, my working hours, I deal
Okay.
with the English language,
Okay.
right? So
Yeah,
after
correct.
that, I am absolutely Bengali. What the
Sure.
storybook I read? Bengali storybook. No English novel. But the movie I see, only Bengali movie. No
Okay.
English. Except if this is a very good one, that's a separate issue. Say, very recently I've seen the Avatar. The only English movie I remember, the Avatar.
Okay.
The many times I do the same movie over and over again. And the only Hindi movie I see, or two Hindi movies I see over and over, more than 10 times. One is the
Okay.
Munna Bhai MBBS and is the
Okay.
Three Idiots.
Oh, okay. Yeah, both are really good movies. Yeah.
Yeah, I have seen it many times. And before
Okay.
releasing them, I have seen Sole maybe 25 times. But
Yeah.
all,
Okay.
all on either the VCR or the recorded, not in the
It
cinema.
is one of the like very, very famous classics. So yeah.
Yeah.
Yeah. I have one last question for you.
Mhm.
Do you remember some incident from your past, probably in your school days or college days, which made you generate and develop an interest in computer science, like general computer science?
No, not a
Okay.
single one from Australia because my schooling was over by 1973.
Okay.
So there is no general concept of computer outside a very few laboratories. Okay, we didn't.
Okay.
We just have some a few of the popular article of one here and there, one or two. We didn't even know those. What can be done with that other than doing some calculations?
Okay.
You know this. You have seen the slide rule.
I'm sorry.
Have you seen the slide rule? Slide rule.
No.
Yeah, I think the recent generations would not have an idea about the slide.
All right. So, look, my entire BTech, I had to do all the calculations on the slide rule. Only in
Yeah,
the fifth year, final year, we just see the calculator, and that is
calculate.
not really that kind of advanced calculator that I can even calculate the sine or cos or this, not even
Okay.
that one, right? So
Okay.
forget about my school days.
Yeah, sure. Yeah. That's all the questions I had for you. I hope those were interesting.
Yeah, surely.
Sure. Vishwas, any closing notes from your side?
Yeah, so Professor Chanda, so it's been a pleasure hosting you, and thank you very much for being part of this webinar series. And I'm very sure participants had a lot to take home about single image dehazing. And I hope that we'll continue collaborating in the future as well, and we'll be glad to invite you to some of our other events in the future. And on behalf of the participants as well as the Computer Society Bangalore chapter, I would like to thank you again. And participants, thank you for your time as well. And Anand, thanks for your time and the rapid fire questions. Always interesting. So thank you, and we'll be in touch with you,
Yeah, yeah,
Professor.
okay. Yeah, and I should thank you for inviting me and for attention given by the audience to hear me. Okay, thank you.
Okay.
Nice to talking to you in the last part. Okay, thanks.
Thanks a lot, sir.
Okay.
Thank you. Thanks a lot.